Welcome back to Integral Calculus. In this video, I want to go through a review of limits. The idea of limits and how to evaluate limits is something that you learned early in your first course in calculus, and it has been long enough from then to now that I expect that you have forgotten more than you learned the whole process. Moving forward, we're going to be applying the ideas of limits to other contexts. So as a step in that direction, I think it's worth taking some time to make sure we understand and remember all of the basics. Let me get my head out of the way and I will dive right in with an example. Let's say the limit as x approaches 5 of x squared minus 3x plus 7. Whenever you are taking a limit of a continuous function, you can always try the approach of direct evaluation. In this case, we just plug in 5 for x. So we have 5 squared minus 3 times 5 plus 7. That's 25 minus 15 plus 7, which comes out at 17. Sometimes when we try that approach, it doesn't quite work. So, for example, if I want to try to evaluate the limit as x approaches 2 of x minus 2 over x squared minus 4, if I try plugging that in, I get 2 minus 2 over 2 squared minus 4, which comes out as 0 over 0. We call this 0 over 0 an indeterminate form. Whenever we arrive at an indeterminate form, it means that the limit process that we chose was not conclusive. It doesn't mean that we were wrong. It means that we have more work to do. Right? So we say that that approach doesn't work, and we go back and we try a different approach. Whenever we're taking a limit of a rational, a common different approach is to see if we can reduce the rational. In this case, we can rewrite x squared minus 4 as x plus 2 times x minus 2, so that the x minus 2's cancel each other out, and now we're taking the limit as x approaches 2 of 1 over x plus 2. And this time, if we try direct evaluation, we get 1 over 2 plus 2, which is 1 over 4, which is perfectly fine. Of course, even that isn't always enough to help us. If I consider this time the limit as x approaches 3 of x squared minus 5x plus 6 over x squared minus 6x plus 9, well, if I try my direct evaluation approach, I'm going to end up with 9 minus 15 plus 6, and then 9 minus 18 plus 9, and that's 0 over 0, again, indeterminate. So we try something else. In this case, x squared minus 5x plus 6 does factor. It factors as x minus 2 times x minus 3. X squared minus 6x plus 9 factors. It factors as x minus 3 times x minus 3. The x minus 3's cancel each other out, but that still leaves us with the limit as x approaches 3 of x minus 2 over x minus 3. And if we try direct evaluation, we get 1 over 0. Depending on context, it might be best to report this as the limit does not exist, which we usually abbreviate DNE. or specifically a 1 over 0 or any number over 0, tends to be an infinite form. So the function approaches either positive or negative infinity as x approaches 3. We could investigate that further if we wanted to. I don't really care enough to do so. Right? Just knowing that this is a stopping point, this is a place where we know that a limit does not exist, is good enough. But I think it's worth mentioning infinity because another common thing that we did with limits is investigate the limit as x approaches infinity. So if we want the limit as x approaches infinity of x squared plus 5x plus 6 over x squared minus 6x plus 9, if we try directly evaluating this, I'm going to put an arrow instead of an equal sign because evaluating infinity is weird. We have infinity squared plus 5 times infinity plus 6 over infinity squared minus 6 times infinity plus 9. All right, well, we have infinity, we square it, we get more infinity, we add infinity to it, we get more infinity, we add 6 to it, we don't even notice, and we get infinity. We have infinity squared, we try to subtract 6 infinities, but we have a square of infinity, so we don't even notice. We add 9, we don't even notice, and we get infinity. Infinity over infinity is another indeterminate form. And the general process, once we have an indeterminate form here, is to try rewriting in reciprocals. Right? The fact that 1 over infinity tends to 0 really makes life easier on us. So in this case, I'm going to take my limit and I'm going to divide by x squared. Because x squared is the highest power of x that appears in either the numerator or the denominator. So I take x squared, divide by x squared, I get 1. I take 5x and I divide by x squared, I get 5 over x. I take 6 divided by x squared. Then I have 1 minus 6 over x plus 9 over x squared in the denominator. And I'm again going to use an arrow here because evaluating at infinity is nonsense, but I'm going to write it that way anyway. So we have 5 divided by infinity. We have 6 divided by infinity squared. We have 6 divided by infinity, and we have 9 divided by infinity squared. All right, the big idea here, when you divide by infinity, you get 0. When you divide a finite number by infinity, you get 0. In this case, that leaves me with 1 plus 0 over 1 plus 0, which is just 1 over 1, and 1 over 1 is 1. I'll leave you with a similar one to try on your own. Here I have the limit as x goes to infinity of 2x squared plus 3x plus 5 over 9 minus 5x cubed. Right? Take a couple of minutes, work through that one, make sure you remember how it works, and I'll see you in the next video.